In this video, we're going to be working AP Pre-Cal Homework 7.2. So we're going to be modeling a bunch of periodic phenomena. So the first one is the daily variation in the apparent position of the sun in the sky can be modeled by the sinusoidal function y equals -20 cosine of pi over 12t plus 30, where y is representing the sun's angle above the horizon in degrees, and t represents the time in hours since midnight. Yeah, that makes sense. That would go up and then down. What is the period of the sinusoidal function? All right, so I'm going to pull out that formula we've been using. Period equals 2 pi divided by b, where b is that multiplier on the inside of the trig function. All right, so period is going to equal 2 pi divided by pi over 12. So that's 2 pi times 12 divided by pi, and that'll be 24. That'll make a lot of sense. T is measured in hours since midnight, and then, okay, 24 hours in a day. So period is 24 hours. What is the maximum and minimum angle of the sun above the horizon in degrees, and when do these occur? Well, I think it would actually be easier for us to do that if we'd already done part C, which is graphing one period of the model. So I'm going to say, all right, down here, it's going to be the minimum, because notice I've got a negative cosine. So that's always one thing about, do I have a cosine, a sine, a negative cosine, or a negative sine? I'm going to graph that standard thing and then fill in the window pane just like we did last time. So a negative cosine starts at its minimum. All right, so, can I connect it with that good curvature, but not obsessing too much over the quality of it? That looks just fine. Okay, so we're going to need the phase shift. Okay, I might start with that. Since we already have the period, the phase shift is 0, since it's just pi over 12 times t. And then the period is 24 hours, so I'm going to put that there. Halfway between would be 12, and halfway between 0 and 12 would be 6. So I would add 6 more to 12 and get 18. That makes a lot of sense, because 18 plus 6 more would be 24. So I feel good about that. Then I go find the midline. That's the number that's added on the outside. That'll be 30. And then the amplitude is going to be 20. So I'm going to go 10 here and 50 up there. Okay. And when do the maximum and minimum angle of the sun occur? This is like up in Alaska when in the summer when the sun never quite goes down. Because it looks like the minimum is going to be at 10 degrees. Let's write that out. At t equals 0 and t equals 24. Unless I'm missing something here. No, 2 pi divided by pi over 12. That is 24 hours ago. That makes sense. Okay, so at t equals 0 and t equals 24 hours since midnight. Yeah, this is, up those very far regions. Okay, and then the maximum is going to happen at t equals 12. That's noon. And that's going to be 50 degrees above the horizon. All right, when it asks us what the shape of the function is at time t equals 5, I think what we mean is the thing increasing, decreasing, concave up, or concave down. So t equals 5, I'm going to say it's right there. So the graph is going uphill and it's concave up. So I'm going to say, increasing. But since I already said it's concave up, I might say increasing at an increasing rate. Okay, so the number of degrees, the apparent position of the sun in the sky, I don't even know how to describe that, that's increasing, and the rate of change of it is also increasing at t equals 5. All right, now, a small boat goes over a series of waves. The rise and fall of the boat as it encounters waves can be modeled by a sinusoidal function. The equation h of t equals 2 times the sine of pi over 5 times t minus 2 plus 1 models the height h of t in feet above sea level t seconds after data starts being recorded. Cool. All right, that makes sense to me. What's the period of the sinusoidal function? So we do the same thing. Period equals 2 pi divided by b, and b is going to equal pi over 5. So I'll say period is 2 pi divided by pi over 5. And if you can just see what this is going to be, great, good for you. But if not, we're going to go over here and do the arithmetic so that we can make sure we can get this right. And that's going to be 10 is the period. So 10 seconds is the period. So for t greater than 0, what is the maximum and minimum height of the boat? Again, I think we need to draw a graph to make these determinations. So I'm looking over here, I'm seeing positive sign. So I'm going to say, all right, positive sign is one that starts in the middle and is going up. Give ourselves the best graph we can manage. Hey, that looks plenty good. And label important values on the horizontal and vertical axes. Yeah, totally. So since I've already got the period, might as well do the phase shift as well. Phase shift is what I'm seeing in there. That t minus 2 means phase shift is 2 seconds. Right, and then the period is 10, so that'll be 12 seconds. Halfway between 2 and 12, we could average those. 2 plus 12 is 14, divided by 2 is 7. And 6, yeah, so that is, wait a second, I feel like I've messed something up there. Period's 10, oh yes, so each of these is going to be 2.5, so 4.5 and then 9.5. All right, and then the vertical shift is 1, okay, and the period is 2, so that'll go up to 3 and down to -1. Okay, and something I didn't do in the last one, but I might do right here, is drawing the actual x and y axes, or I guess in this case the t and h axes. Okay, but I think that's nice for us to do that there, because we can see then for just a little bit of time the thing is dipping underneath sea level, which makes sense because it's going over a wave, and a wave's gonna have a low point too. So where are the maximum and minimum heights of the boat? And when are those first occurring? Okay, so notice that we're only looking at starting at t equals 2, so we should probably make sure there wasn't a minimum happening sometime before that. Okay, but if we had extended this one more square over, we'd see, because we know that each square is 2.5 units of t, that we'd gone back before the h-axis back into negative t values. So if I was to extend the graph, that first minimum would be happening in negative time, and we said for t greater than 0. So we're going to ignore that and say the first maximum is going to happen at t equals 4.5, and the height would be 3. And then the first minimum of the height of the boat is going to be t equals 9.5, and the height there would be -1. Right, and then if they asked what would be the behavior of the graph of h during the time interval 13 to 14, we'd need to extend the window one more time. But I don't think we necessarily need to extend the grid. I think we just extend the graph, right? We know what's going to happen. And so between 13 and 14, that'd be kind of through here, and t, that'd be up here. We're increasing concave down. And so I might say increasing at a positive rate. I mean, well, it is increasing at a positive rate, but it's a decreasing rate. All right, the next example is a Ferris wheel ride. So you climb into the car on the Ferris wheel ride, and the graph below models the height in feet of the car on the y-axis t seconds after the ride begins. And I might say, it can be the t-axis. We just had one like that. We're going to answer these questions. What's the period of the Ferris wheel ride? So I normally look top to top, but we don't have that much graph to look at. So I'm going to look at, see two labeled points that are both bottoms on the graph, and we just need two equivalent points to measure the period. So it's going from t equals 0 to t equals 80. So I'm going to say the period equals 80. And because I know eventually, we're going to need to write some equations down. I'm going to just go ahead right now and say, all right, period equals 2 pi over b. 80 equals 2 pi divided by b. So I'm going to multiply both sides by b. Divide both sides by 80. So that's going to be pi over 40. Okay, so I'll need that later, I'm sure. What's the amplitude of the Ferris wheel ride? Okay, well, the amplitude is going to be the distance from the midline to one of the extremes, but we don't have the midline labeled. So what I might do is I might take the vertical distance from the maximum to the minimum. Okay, so the maximum was at 75. The minimum was at 5. So the midline would, or I guess I'm looking for the amplitude, so that'll be, what was it, half the difference. So 75 minus 5, yeah, that's the height divided by 2. So half of 70 is 35. But because I need that midline eventually, I should probably just go in and find it right now. And the height of the midline will be the average, so 75 plus 5 divided by 2 is going to equal 40. And that looks believable based on the graph and where I drew the midline. So I know that that means that, you know, these numbers, 80, 35, and 40, those are kind of going to be set on both of these models. What's going to change is the phase shift, so that C value. So I've got A equaling 35, B equaling pi over 40, and this 40 here, that's going to represent D. Okay. So when I want to write a cosine, I already know y is equal to A is 35 times the cosine of B was pi over 40 times t minus something plus 40 on the outside. Now you got a couple of options, right? There's more than one right answer. If you wanted to say, okay, well, this thing's starting at the bottom at t equals 0. Oh no. Every time. And if you wanted to say, hey, I'm starting here at the bottom at t equals 0, that's a negative cosine. You could just, you know, do the phase shift with 0 and slap a negative onto that 35. Okay, but I think that the thing that I'm going to do most often is just, if we're doing a cosine, we know cosine wants to start at the top, normally. So I'm just going to make that the phase shift. So I'm going to say, all right, phase shift is 40, because that was the t value of the relative maximum that I can see. And I'll just go from there. Okay, and I think that'll be the way to go. And then as far as the sine, I mean, kind of the same idea. Y is going to equal 35 times the sine of, okay, the pi over 40 is set because the period is set. It's just going to be a question of phase shift. You know, so is the vertical shift. That one's set. So sine, you know, that one we're used to that one starting where it's coming up through the midline. So that would be right here. And that's going to happen halfway between the minimum and the maximum. So the minimum happened at t equals 0, and the maximum happened at t equals 40. So that halfway in the middle spot, that's going to be at t equals 20. And I'm going to make that the phase shift because that's where, you know, my normal idea of sine is starting there. All right, the next one's talking about a sound wave, and I'll be honest, I don't totally understand, you know, like what this, the pressure of a wave even totally means in terms of my, you know, user experience of a sound wave, you know, hearing it. But that's okay. That's kind of part of the message here is that, like, yeah, some of the things that we're going to model with trig functions you might not have, like, already studied in science class, but it doesn't really matter. Just mathematically, you're going to use the points that you're given on the graph and your knowledge of trig functions to kind of put this all together. If we've got a graph, we can figure out anything they're going to ask us about it. So what's the period? Easily, right? We need to look at, I mean, the two labeled spots, I think we're going to have to use that. But both of these are places where the graph is coming up. You know, like, we would think of the beginning of a y equals sine x graph. And so that distance there is the distance from pi over 3 to 5 pi over 6. So I'm going to say, I'll do that over here. Period equals, I'm just going to do right minus left, 5 pi over 6 minus pi over 3, I might call that 2 pi over 6. That's going to equal 3 pi over 6, which is pi over 2. Now, because just like last time, I know I'm eventually going to have to write an equation for it, I might as well find the value of b. Okay, we know that period equals 2 pi divided by b. So that's going to mean that pi over 2 equals 2 pi over b. And so you could solve this one with your eyes maybe, or you might cross multiply. Either way, you're going to get b equals a half. No, a fourth. Okay, I should have tried to solve that one with my eyes. Yeah, b times pi equals 4 times pi, so b is equal to 4. Yeah. I think I said it wrong even the other time. So maybe I should have cross multiplied. They're going to ask, what's the amplitude of the sound wave? Okay, well, it looks like, okay, from the two labeled points that were equivalent, we have to assume that's the midline. And it looks like it's going, yeah, up to +2 and down to -2. So I'm going to say that the amplitude of this thing is 2. Amplitude equals 2. And now we're going to maybe also point out that the midline is 0 there. So I'm going to say that means d equals 0, so y equals a is 2 times the cosine of b was 4 times t minus, we'll figure out the phase shift in a minute, plus d is 0. And I'm going to even write that in. Okay. Normally I wouldn't, but I think just like to emphasize where all this is coming from, because this is all pretty new. Might just add the +0 on the outside. So the phase shift, we're saying, okay, well, if we're using a cosine, we're looking for a maximum. Okay, that would be up here. Okay, I don't know what this minimum is, this maximum is over here that's less than 0. You could use that as the phase shift as well if you wanted to figure that out. But I've got the pi/3, and it's really not that far off to go to the maximum from the midline. I know that's a quarter of the period, and so I'm going to go from there. The period was pi/2, so a quarter of that is going to be pi/8. Okay, so the x-coordinate, or the c-coordinate, I guess this is going to eventually go in this cosine, but the x-coordinate of that maximum, so x0 is going to equal the phase shift for sine, pi/3, plus a pi/8. So in terms of 24ths of pi, that would be 8 pi/24 plus 3 pi/24. That's going to be 11 pi/24. That was kind of rough. But if I'd gone backwards, I'd have had to subtract 3/4 of the period, so it would have been like kind of a similar level of computation there. So I'm going to say, all right, 11 pi/24. I don't think I left quite enough room for that, but there you go. That'll work. Okay, and then write an equation in sine that can model the situation. So that'll be a times the sine of b times t minus some number plus d, which was 0. Right, and like sine, we had the place right there labeled where it was coming up. That was pi/3. So I'm just going to put that in there and move on. All right, next we've got one that's giving us a table. Like that, that's something different. So the population of a certain type of bird on an island is tracked. The table below gives the population P of T at the beginning of the month after data starts being tracked. Data can be modeled by a sinusoidal function and will continue to follow the pattern established to answer the following questions. Okay, so what is the period of the model? Okay, well, I think maybe we should, kind of take a step back and look at the data. It's going from 500 to 350 to 200, back to 350 to 500, and then back down to 350 and 200. Okay, so it looks like the maximum is 500 and the minimum is 200. And, yeah, and the repetitiveness, the fact that it's coming back to... And now, if you looked at the 350s, yeah, it's repeating the 350s every 4 seconds. I think it meant to say T days. Yeah, it's got to be. This is a population where there's going to be a lot of birth and death, it looks like. But yeah, I think number of, it doesn't say, but it's going to be days. Okay, so the period of the model is going to be 500 to the next 500 is going to be 0 to 8 is 8 days. And then once the amplitude of the model, well, that would be half the difference between the maximum and the minimum. Maximum is 500, minimum is 200, it's a difference of 300, half of that would be 150. An equation, okay, so that 150, that amplitude, that'll give me A. Period equals 8 is going to give me, okay, 8 equals 2 pi over B. 8b equals 2 pi, divide both sides by 8, b equals pi over 4. Got A and B. I guess in order to find the value of D, I'd have to average the maximum and the minimum. So that's 500 plus 200 divided by 2. That's going to be half of 700 would be 350. All right, so I've got 3 of them. I just need to figure out what C is, but I'll kind of do that after filling in most of the other pieces. So 150 times the cosine of B was pi over 4 times t minus some number plus the 350. Okay. Cosine, let's start at a maximum. Okay, regular cosine if we don't want to make it negative. So we look for the maximum for our phase shift. It started off at t equals 0 being at a maximum, so that's fortunate for us. We'll just write that in there. And then for a sine equation, 150 times the sine of pi over 4 times t minus something else plus 350. All right, so sine, our standard idea of sine is it's kind of coming up through the middle where it starts. So we're looking for that phase shift right there to be a place on the midline where the function's increasing, whereas p increasing at 350 right there. So I'm going to use t equals 6 as the phase shift. And you may be noticing like, oh, like if I've got a phase shift for cosine, I could just add like 3/4 of the period to get a phase shift for sine. And I mean, I'm pretty sure that is true. Or 3/4 of a period. I think I might have said 3/4 of the phase shift. But, it might be true, but I don't think that's really worth memorizing. I think just like looking at it and knowing about your standard sine and cosine graphs is the way to go. So now here we got another table. So I think this one will be pretty easy to navigate. Oh, except I was confused about this one. Okay, I kind of have my doubts about the shape of this graph, but I am going to notice the maximum and the minimum and the fact that it's, oh man, it's going from 10 to 2, and then it's going 9, 6, 3, and 3, 6, 9. I don't know if proportionally speaking that's possible for a sine or a cosine, but maybe it is, and I'm just not thinking about it right. But I'm going to say that this looks like half the period from this, because this is a maximum, and this appears to be a minimum. So I'm going to say that half the period is 1 to 5, which is 4, so the period is going to equal 8. In the last example, the period was 8, and we saw that b was equal to pi over 4, so I'm not going to go through that whole thing again. The amplitude of the model, well, that's going to be half the difference between the maximum and the minimum. Half the difference would be half of 8 is going to be 4. And the midline, which is going to give me the value of d in the model below, is going to be 6, halfway between 2 and 10. And so y equals a cosine of b times t minus, okay, for cosine we're looking to start at a maximum, so that'll be t minus 1 plus the midline was going to be 6. Then if I try to do the same thing, okay, for the sine graph, just like I said before, if I was looking over here, I'd be looking to be in the middle going up. So that would probably be at a 6, but where it's increasing, so that'd be right there at t equals 7. So y equals 4 times the sine of pi over 4 times t minus 7, and then plus 6. All right, now we've got a bowling ball attached to a string in a frictionless environment. And let's see, I was trying to see how many more of these we've got. Looks like just these last 2. All right, so yeah, these definitely are sine and cosine. They're going back and forth in a frictionless environment. A pendulum, I think theoretically would just keep going forever in a frictionless environment. Swings freely, obtaining a maximum distance from the wall of 20 feet. Okay, ball will return to its starting position of 0 feet from the wall 3 seconds later. Okay, so they've given us the period. Yeah, we're not talking about the frequency yet. We'll talk about that next time. but I am going to draw in on this diagram. That's going to be the wall. And so the minimum distance would be 0 feet from the wall, and the maximum distance, they said, was 20 feet. So the amplitude is half of the 20 feet is going to be 10. Period. Okay, so return to its starting position of 0 feet 3 seconds later. Okay, so let go at t equals 0 at the wall. Return to the wall after 3 seconds. Period equals 3. Period equals 2 pi divided by b. I'm not going to trick myself into thinking too hard on this one. B is going to equal 6. Okay, so, and no, it's not. I don't know why I just keep messing that up. Okay, so we're going to go over here. We're going to do some cross multiplication. 3b equals 2 pi. And then b is going to equal 2 pi over 3, pardon me. So we've got b, we've got the amplitude, the midline is going to also be 10 because, yeah, it's going from 0 to 10 to 20. All right, and 10 is halfway in the middle. So graph 1 period of the distance of the bowling ball from the wall. So it's starting off 0 feet from the wall, and then it's going to increase to its maximum and then decrease back to its minimum of 0 feet. And so I'm going to want to use just a negative cosine. Okay, we could phase shift by whatever we determine that spot in the middle to be. Okay, but I think, oh wow, whoops, that was too bad. Not to be perfect, but I think it needs to be a little better than that. So I'm going to just say, all right, y equals a is 10, but I'm going to make it a negative cosine of 2 pi over 3t. And I'm going to have a phase shift of 0 because I'm starting a negative cosine graph there at t equals 0. The period was 3, so that'll be 1.5. That'll be 75, and that'll be 2 1/4. Right, and then for sine, I'm going to be looking for a place where it's at the midline and coming up, so that would be right there. Phase shift of 0.75. Y will equal positive 10 times the sine of 2 pi over 3 times t minus 0.75. And then I forgot to add the 10 on the outside on the first one, but I'll do that there, and they're both good now. Right, and then number 8, the last one, electricity consumption in a given city can be modeled by a sinusoidal graph. On a given day in the winter, it's at a minimum of 40,000 megawatts at midnight. So this is another one starting off at a minimum of 40, and that's going to be t equals 0. Rises to a maximum of 52,000 at noon. Okay, so that's t equals 12, and going to be a maximum of 52. Then returns to the minimum at midnight. T equals 24. Right, and so we're just going to fill in the other points. Right, sinusoidal graph. This one's going to be very similar to the other one, but maybe unlike the other one, I will phase shift the cosine instead of just starting with a negative cosine graph. But you can do whatever you want. We'll be ready for both of those on the quiz and on the test and whenever, even on the free response section of the AP exam. Those you'll see in the next lesson. You're going to have to do kind of something like this, and there's going to be a variety of right answers, and we're going to be ready for all of them. Okay, so halfway in between the 40 and the 52, notice they didn't really give us a table or a graph, just like we're having to intuit all these things from the statement of the question. And that's part of the course. There's a paragraph that you have to read through because, you know, that type of extraction of relevant information from a written statement, that's part of modeling. That's the logic there, and so we need to be ready for that. So halfway between 40 and 52, that's a distance of 12 would be 6. So 46 is the midline. All right, so I'm going to say d equals 46. The distance from the midline to each of the extremes is the amplitude, which is 6. The period is going to equal 24 hours. And it's been a while since I think that was the first one. But it's going to be 2 pi over b. Okay, 24b equals 2 pi, and so b will be 2 pi over 24, which is pi over 12. Okay, I did already do the graph of one period. I'm going to go ahead and sketch axes as well because I like to do that. That's going to be the electricity consumption, which I'm just going to call Y, versus T, which is, let's see, definitely going to be down here, and this graph is not going to be drawn to scale, but that's all right, right? It's definitely up there in the first quadrant. All right. So did that, labeled all the stuff I needed to. I'm going to just write in my equation. So y equals amplitude cosine of b was pi over 12. T minus, okay, for a cosine, I'm looking for that maximum. That was t minus 12. Plus the midline was 46. Okay, and then for a sine, I'm looking for one just like before that's coming up through the midline, so that'd be right there at t equals half of 12 is 6. And so y equals a times the sine of b times t minus c plus d was, again, 46. Yeah, same midline. All right, and what is the shape of the consumption graph at t equals 9? Okay, that would be right here between 6 and 12. The graph is increasing and concave down, and so we would say increasing and concave down or increasing at a decreasing rate. You know, because it kept asking about places where it was increasing, and I know that y'all have most of the issues making these decisions. I'm having a hard time keeping it on the screen. Places where things decreasing, I'm going to do a couple of extra examples, and I might ask you, I'm going to just bring those in right now. All right, so just think about it. What about on 14 to 17? You know, you've been with me this long, so with me a few seconds longer. What's happening to the rate of change here? Okay, on 14 to 17, okay, we need to figure out what's halfway between 12 and 24. That'd be 18. On 14 to 17, that's clearly in that third interval. I'm decreasing and concave down, so it'd be decreasing at a decreasing rate. The rate of change would be negative because the graph is going downhill because the function's decreasing. And the rate would be decreasing because I'm decreasing at a decreasing rate. Now, if I'd asked you about something like the interval 19 to 21 or something, okay, we'd be decreasing at an increasing rate because the graph is going downhill and smiling, it's concave up, something like that. Okay, so that's going to be all for this video. Thanks for watching.